Alright guys, it's Mr. Riz. We're going to continue this chapter. We're going to be on section 1.4, which is continuity and one-sided limits. We're going to take two videos on this. The first part is just a lot of vocab. Alright, so first we'll look at continuity on a point on an open interval. Alright, so in mathematics, the term continuous has much the same meaning as everyday usage. Informally, to say that a function f is continuous at x equals c, it means there's no interruption in the graph at f at c. That is, the graph is unbroken at c. There's no holes, no jumps, no gaps, no vertical asymptotes, no nothing. It's just a line that goes all the way across. Alright, so if we look, there are three different ways a function could be not continuous, or three things that needs to happen. First, those three things are: the function needs to be defined at f equals c. So there needs to be a point at f of c. Second, the limit of f of x does not exist at x equals c. So that means all limits, or you must be able to go towards, so you can't have any jumps in the graph. Part 3, the limit of f of x exists at x equals c, but is not equal to f of c. So we need to make sure that we have a limit that equals where the point is located at. The previous page shows those three examples of that do not meet. Alright, so you need to make sure f of c is defined, that the limit exists, and that the limit and the point are the exact same thing. So that will work. That would be a continuous function on the open interval, and so that'd be everywhere from negative infinity to infinity. Alright. Well, next there are two types of discontinuity we can talk about. There is removable discontinuity and non-removable. Removable discontinuity is, say, what we've been working on. Say there's a hole in the graph that we could just get rid of if we could just figure out an equal equation. Non-removable is if we have a jump in the graph, or if we have like a vertical asymptote. We can't get rid of that vertical asymptote. There's no way we can put a point at that x equals c to make those two graphs, two parts touch each other. So here, if we look at these three examples that we talked about before on this open interval, this is removable discontinuity because we could have a function that goes exactly right over it. This is non-removable because we can't get rid of that gap. Now this last one is removable discontinuity. The reason why is, if we think of this, this would have to be a piecewise function to have a completely different point. So we can remove that part of the piecewise function. And just like the last one, we could find a function that covers up that hole in the graph. Alright, so let's go ahead and discuss each type of the continuity in each one of these functions. So go ahead and write it down, and you can pause the video and we'll move on. Okay, the first one of x equals 1 over x, f of x equals 1 over x. This is non-removable discontinuity because there's no way that we can change the function to get rid of that x on the bottom. And if we were to graph it, we could clearly see that there's a vertical asymptote at x equals 0, and we can't get rid of that. So f is continuous for all points except for at x equals 0, which we have non-removable discontinuity. The next one, g of x equals x squared minus 1 over x minus 1. Now this is removable discontinuity at x equals 1. The reason why, because we can replace x squared minus 1 to x plus 1, x minus 1, and we can remove that hole in the graph. We can remove the discontinuous point. So it's removable discontinuity. Next one, if we were to graph this piecewise function, we would notice that as we are going to this point, and the first one would be a closed dot, and then we'd have an open dot right on top of that for the second graph. The open dot and the closed dot are the exact same point, and so there's no jump in the graph, the limit goes to the same location and that point is defined. So this is continuous across the whole number line. Y equals sine of x, although it does alternate and we never get anything above a 1 or a negative 1, all points on the x do exist. So that is continuous across the whole number line. Next, one-sided limits and continuity on closed intervals. So closed intervals are different. It's when we start looking at specific things like from all the way 1 to 5. Okay. What we want to do is look at, sometimes we'll approach a limit just from a specific location. So if we ever want to do, or if we ever have a x approaches c plus, that means we're going to be looking as we go to the right. Now if we ever have a negative after the c, we're going towards the left. And so sometimes we can have completely different values depending on if we're going from the left and from the right. So here we go. One-side limits are useful for taking limits into functions that involve radicals. The reason why that is because radicals have non-removable discontinuity. If we were to graph that, we would more likely have a function that just starts at 0 and has positive values but doesn't have any negative values. So if we try to go to this from the left, there's no points on the left to go to that. So with square roots or radicals, we need to make sure we're left, depending if it's positive or negative. So here we can look at the removable, or we can look as the limit approaches -2 from the right, because we have values to the right of -2. And we can see it's going down towards 0. We couldn't do it from the left because there are no points. Same thing with the other side. We can go to 2 from the left, but we can't go 2 from the right. There are no points there. So what we could do is talk about the existence of a limit. And basically the limit exists if it goes from the left and from the right. Alright, the concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when it's continuous in the interior of the interval and exhibits one side at the endpoints. This is stated more firmly in the next definition. So, if f of x going from a to the positive equals f of b, and f of x going to b from the left exists, that function must be continuous across the whole interval. So if we look at this function, well, once again, we know we have a radical, and we're going to look at the closed interval from -1 to 1. Now we're only looking at the closed interval, so we could care less of what's, -2, -3, -4, or numbers higher, 5, 6, 7, 8. When we graph these, we can look, we have continuous points between that closed interval, and going from the left to -1, or coming from the right from -1 and coming from the left of +1, we can see this function is continuous. Alright, the next one we'll actually do some problems that are a little bit more difficult, but if you have any questions, good luck on this section.